And today what I'd like to do is round out Chapter 4. And Chapter 4, Section 4.8, talks about antiderivatives. And not in the sense that, anti like you're against, although you very may well be at this point antiderivative. This is the antiderivative from the standpoint that if we take the derivative of a function, let's say we have this function capital F, and we take this derivative and get f at x, we say that capital F at x is the antiderivative of f at x. Okay, so in other words, the antiderivative is if that was the original function and the derivative is the derivative, then there's that relationship of going backwards. And so the thing that we're going to talk about today are antiderivatives and kind of undoing differentiation. And we're only going to do it really with polynomials at this point. What this is going to lead into, we're going to take a little bit of a side path or side trip on Monday to talk about something that's called Riemann sums. And the Riemann sum is a way to calculate the area under a curve. Like right now we've taken a curve, a function, and we've talked about what's the slope of that thing along any point along the way. We're going to talk about what's the area under curves and what that means on Monday and Wednesday. And by the end of the week next week, we're going to be relating antiderivatives to integrals. And the integral is the area under a curve. So we're going to round out the semester with an introduction to integration. And if you love derivatives, you'll really like integrals. And the converse is true too. If you thought derivatives are annoying, integrals will especially annoy you. So anyway, we'll try and take it a step at a time and get you a good start here. So we're talking about the antiderivative, and so if we have this function y equals x squared plus 2, and we take the derivative, of course we get 2x, right? And the thing of it is that if I take other functions that are similar to each other, and here I'm not making a distinguishing, I'm just saying, y could be x squared plus 3 or y could be x squared plus 7, they all have the same derivative. All right, so the first thing that this says is that y in each case is the antiderivative of 2x. Okay, so the first thing that I want you to become acutely aware of is that the antiderivative is not a unique function in the sense that if we just take x squared, you might say x squared is the antiderivative of 2x, but in fact there are many antiderivatives of 2x. Now the differences between these antiderivatives is just the constant term, right? Because when you take the derivative of a constant, you get 0. And so that 0 disappears whenever you take it, or the constants disappear whenever you take the derivative. And so if you're looking at the antiderivative, you can have this function that is quite specific, in this case it'd be x squared, but you have this, this constant that you need to add to it. And for the generalized form, we'll just call this c. And so we'll say the antiderivative is going to be this function plus c, and c is any arbitrary constant. That means it really is arbitrary. You can choose any number that you want, and in general, unless you have a basis of choosing a number, you don't choose it. You just basically say it's c. And this is one of the things that's one of the easiest things to forget when you're finding antiderivatives is to put the c at the end. Okay, so let me run you through a few antiderivatives. So if we have, just remember that we're looking for capital F. So when we differentiate capital F, we'll get our function. So I already talked about this one. If our function is 2x, then the antiderivative is going to be x squared plus c. Now if we have just x, what do you suppose the antiderivative is? Okay, so you think to yourself, if I take a derivative and I end up with x, what did I start with? All right, so I'm going to start with 1/2 x squared plus c. Okay, so look at that derivative, or look at capital F. If we take the derivative of 1/2 x squared, we get 2 times 1/2 times x, which is just x. And then, of course, we have our c. So this is going to take a little bit of concentration in terms of anticipating what you're going to end up with after you take the derivative of something. And I'll have a general formula for you to show you on the next chart. But for now, I just want to kind of look at these, look at some functions and think in terms of what would I differentiate to get to the function that I'm given. So if I have something like 4x cubed, what do you expect the degree of this antiderivative to be? 4. Okay, so if I take x to the 4th and take the derivative of it, I get 4x, right? So that would be that would be the way to discern what this antiderivative is, and always you add c. So if you have just another constant, or if you don't have a constant or another constant, when you have something like x cubed, you're going to expect to have a function that has a degree 1 higher than x cubed. And so if I start with x to the 4th and I want to end up with 1 as a coefficient, of course I'm going to have the coefficient of my antiderivative is going to be 1/4. So when I take the derivative of 1/4 x to the 4th, I get 4 times 1/4 x to the 3rd. So it'll be x to the 3rd.
So the antiderivative is just like working backwards?
It is. It is exactly working backwards and anticipating that we have, and of course I went a little too far on that one. If I, let me back up here. So all the rules that we've learned from differentiation really have, you can essentially undo them to find the antiderivative. So when we have a polynomial like this, where it's x squared plus x plus 1, we'll have the same thing that we had before, where the antiderivative of the sum of functions are going to be the sum of the, or you can take the derivative of the sum and get our original polynomial. So we can we can find the antiderivative term by term on this thing. And so we know that when we have x squared, what we want to do is we're going to get 1/2 or 1/3 x cubed, right? Because if I take the derivative of that, I get x squared. The next one, you can see I get 1/2 x squared. We found that one before. And then the antiderivative of 1 is x, right? Because the derivative of x is 1. And then we have our constant c. So we can go along a polynomial and any sum like this and look at the antiderivative of each individual term and add them all up and then get the antiderivatives. So it's possible to state all those rules that we had of differentiation in terms of antiderivatives, but just think of them as working backwards. We don't have to state them explicitly. It's just that the sum of these things work as well as just taking the individual terms. Okay, so if we have something that has, let's say, arbitrary constants in front of it, we have to then come up with the constants, the new coefficients that are going to make this thing work as an antiderivative. So on the first one, we expect of that 3x squared, we expect the degree to be 3, right? And so if we take the derivative of x cubed, we get 3x squared. So on this particular one here, that first term of the antiderivative is just going to be x cubed, right? And so with 2x, we get kind of a similar thing. Well, we already know that the antiderivative of 2x is x squared, so that coefficient's going to drop away. And then 5, that's a constant. And so if we take the derivative of 5x, we'll get 5, and we add our c at the end. Okay, is everybody following? So this is really a matter of undoing your derivatives. Okay, so let's generalize what this rule is. Just like we had the power rule, we can state the power rule in terms of an antiderivative. So what we're doing with the antiderivative is we're taking as the coefficient 1 over n plus 1, and then having the new degree as n plus 1. Okay, so why don't you try this? Try taking the antiderivative of this now, of these two. I'll give you a few minutes on this to think about it and talk about it. But think about what it would take to get those coefficients. Those coefficients aren't exactly won't exactly work out, either disappearing or to be, some simple number or so. You might get a ratio on it, but see if you can reason what those coefficients will do. Okay, so what was the first step you did there? Multiplied it out. Okay, one of the things about finding antiderivatives is that you remember we had things like the product rule and the chain rule and things of that sort where we would get multiple things. It's going to be a little bit more difficult to go backwards now, because think about undoing the product rule where you would essentially need two different products to collapse into one product, right? Because with the product rule you get two products out of a product. The chain rule, we not only get a function that has this outer derivative, it's multiplied by the inner derivative, and so this thing kind of telescopes out. We're going to have to, collapse it back in. So anytime we can, we want to extend these things to be just polynomials, because we do have a rule for polynomials that's fairly manageable. And so the thing that we want to do is expand it and then find the antiderivative. So the first term is going to be 2/3 x to the third. So if you imagine differentiating that, you get 2x squared, right, which is what we're looking for. Second one is 1/2 x squared. And then the third one is negative x. And then, of course, we have our plus c then. Okay. Any questions? All right, so we'll do a few more, and we'll get a little bit more sophisticated. Now with fractional exponents, the power rule still works, right? So we're going to have to think about how we're going to have a generalized approach to this, so we don't get messed up. So our strategy is going to be taking first, figuring out what your exponent should be. So we take that 1/4 and we add 1 to it. All right, so we add 1 and then we figure, okay, if we take the derivative of it, what do we get? We get 5/4 x to the 1/4, but what we really want is 5. So if we take the coefficient to that thing is to be being 4, all right, then when we take the derivative of it, the 4 and the 5/4, it multiplies out to 5. Second term the same way. If we first look at what the exponent should be, it should be 1 plus 3/4. And so you think, okay, you need to get to a 7 by taking the derivative. And so if we take the derivative of this just the way it is, we get 7/4. We want a 7, so we know that we have to have a 4 there. And of course we add our c then. All right, so my suggestion here on this, on these kinds of things is first work on the exponent, and then if you get the exponent right, then look at the coefficient to see what the coefficient will be. I think, when you're going left to right and taking the derivative, you first calculate coefficients and then you subtract 1 from the exponent. You want to do exactly the opposite now. You want to add 1 to the exponent, and then you want to work on what your coefficient is going to be. Okay, so if we have expressions involving radicals, the approach is the same. we put the, except that we put the radical into fractional exponential form. So the first thing we'll do is we'll restate this as 6x to the 1/2 minus x to the 1/6. Okay, so then we look at this the way we did before, where we take this, the new exponent. We know the x to the 1/2, 1/2 plus 1 is 3/2, and so we're going to have that 6 as a coefficient in some fashion. So what we'll put here then is the we should have a 2/3 multiplied in here. So if we take the derivative of x to the 2/3 times 2/3, we'll get 1 and then have the 6. So when we simplify that out, we'll get the proper coefficient. And then we'll look at the next one. We say, all right, x to the 1/6 has a coefficient, or has a new exponent of 7 to the 6th. Excuse me, I'm tongue-tied today. The new exponent will be 7/6, and so we know that that coefficient will have to be then 6/7 in order to just to get a 1. And so then we'll simplify this out, and we get our antiderivative like that. Okay? All right, so then the last one. Here's the case where we have 10 over x to the 9th. So the easiest way to handle this then is to make it look like the other ones where we can use the power rule. So we'll take a negative exponent to make this a little simpler for us. And so we have 10 x to the negative 9th. And so when we take the when we find the antiderivative, we're going to add 1 to negative 9, so our new exponent is negative 8. And then we're going to have to say, okay, when we take the derivative of that, it's going to give us negative 8 as a coefficient, so I'm going to take negative 1/8. And so when I simplify this out, I get negative 10/8 over x to the minus 8. And then if I simplify that further, I get negative 10 over 8x to the 8th. And let me see, did I simplify that? I didn't simplify that once more. Of course, we can reduce that fraction to 5/4 as well. Okay, so is everybody following that? All right. So here's a few for you to try now that are in a different form than, well, there's just a regular polynomial, but we have a few that are in a slightly different form than what we've had before. So go ahead and try those. Okay, did you get an answer? Somebody get an answer? All right.
I got 2x squared minus 4/3 x squared. No, I did that wrong. No, okay. X to the 3/4. No, I didn't even simplify. Yeah, I'm reading the wrong one.
Okay, you read the wrong one. Okay, yes.
I got 1/4 x to the 4th minus 4/3 x cubed plus 2x squared plus c.
Plus c, that sounds really good. Let's compare it with what I got here. First step, of course, is to expand it. And then once you've expanded it, you do it term-wise. And so the first one, we get 1/4 x to the 4th. Oops, gosh. And then the second term is 4/3 x cubed plus 2x squared plus c. Okay?
I did it backwards, like when I backwards, I had 2x squared minus 4/3 x cubed plus 1/4 x cubed.
Okay. Yeah, you know, it's one of these things where once you learn how to do things one way, like taking the derivative, that's easy enough to do once you master it, but then you learn to undo it, and then, you know, you always have to remind yourself of which direction I'm going. It's kind of like, you know, either factoring or expanding things, or, you know, taking, you know, of any function, whether you're doing it or undoing it. Okay, how about this next one? What is it, what would be the first thing that you would do here? Okay, did you get the exponential form?
Yeah, I got x to the 3/4 plus x to the 4/3.
Great, okay, so that works out like that. All right, and then we take the antiderivative. Did you get that part?
I'm really close to finish.
Okay, I'll let you finish, and
And then I got 4/7 x to the 7/4 plus 3/7 x to the 7/3.
great, okay, 4/7 and 3/7, so the new coefficients plus c. Okay, everybody follow there? And then, of course, always take the derivative to convince yourself that you did it right. So if you take the derivative of that first term, you know that it's going to be 7/4 times 4/7 to give you the 1 for the coefficient up here. Okay? And then you subtract 1 from 7/4 and you get 3/4. So that works. Now this last one, the way we do this is the way that I've really tried to encourage you to even take derivatives, where instead of having a ratio, you know, and like if we were taking the derivative of this, not to use the quotient rule, but first simplify it into the sum of terms by dividing through that x, the square root of x. And so, anybody do that and get that simplified there? Yes, you got that again? Okay.
The answer or the simple?
The simplification first.
I got 6x to the 5 halves minus 2x to the 1 half. Or did I leave it?
I think I dropped my 2 there. In fact, you got it right. I didn't. So let me make a correction here. So this was a 2, right?
Just my notes.
All right.
And then for my final answer, I got 12/5 x to the 5 halves minus 4x to the 1 half.
Okay. So I went through this process of just keeping my 6. And then the other thing that I need to do here is add my 2 in. So I got 2 times. And then this goes to,
So wait, are we always just multiplying by the reciprocal of the new exponent? Is that, okay, that's a rule, okay.
and that of course is wrong here. Okay. So let me dial back based on that question here. If we look back to the rule here, you see how we take the antiderivative, the new coefficient of the antiderivative is 1 over the new exponent, right? And so whenever you have a coefficient that you're starting with over here, that thing just gets retained on through. So in other words, if I have, let's say, f at x equals cx to the n, my antiderivative then is going to be c, I'm breaking chalk here, c over n plus 1 x to the n plus 1. So the way I've been doing it here is to show it as two products. So I have c times 1 over n plus 1. And then simplifying this as my last step. So if this turns out to be a ratio, of course, this is just the reciprocal of the ratio. So if I go back to the ones that we just did, you can see that that's exactly what happens when perhaps the page before has that a little bit more. Yeah, so this one really shows it where I'm taking the reciprocal of the new exponent and then simplifying it out, and that should be actually 5/4, 5 over 4x to the 8th. Okay, so let's look at now second derivatives. Now second derivatives, you do exactly as, if you want to find the function, you do it exactly as you would with finding the antiderivative of the first derivative.
What was the answer to the last one?
That was 12/5 x to the 5/2 minus x to the 1/2.
Oh. Plus C.
Plus c.
Thank you.
Yeah.
On the third, on the last one, the third example,
Mm-hmm.
it says x to the 3/4. Why is there a 7 in the answer for that part? I don't know where the 7 comes from. I get where the 7 comes from in the second half.
Sure. Because what I'm going to, the new exponent here is 7/3
Yeah, but on the other one.
on the next page, or this?
No, yeah, the first part of that problem.
Okay, so I have 3/4, and I'm going to add 4/4 to it. So I get 7/4. Okay. If there's no other questions, we'll go on. So I'm going to find what the function is based on knowing the second derivative. So I'm going to find two antiderivatives here, right? First I'm going to find the antiderivative that will give me the derivative of f, and then I'm going to find the antiderivative to give me f. Okay, so this one here, the derivative now is the derivative of the, we look at this x, and the new exponent is 3, and then that's going to be times 1/3 this coefficient, so I get 4. So take the derivative of this just to convince yourself it's right. The derivative would be 3 times 4x squared, so that's exactly what we want. By the same kind of reasoning, my new exponent here is going to be a 2, and then if I multiply 6 by times 1/2, I get 3. So there's my my new coefficient. Now I want to find the antiderivative again to find the original function. But here there's a little thing that crops up in that I have c, and I can't just ignore c until the end. I have to include the fact that I have a c here. And so when I find the original function, I have actually two c's in here. So first, let's take the antiderivative of 4x cubed. That's going to be x to the 4th, right? Because the derivative of x to the 4th is 4x squared, or 4x cubed. I think I'm saying a lot of things wrong, so I apologize if I'm twisting around some numbers that I'm showing here. The antiderivative of 3x squared is x cubed, because if we take the derivative of x cubed, we get 3x squared. And so then we have to take the antiderivative of our first constant. And I'm going to label this C1 just to distinguish it, because it's not the same constant that I'm going to add on here. I get C1 times x, which is the derivative there. And then I'm going to add on the constant that I need for taking the second antiderivative. So every time you take the antiderivative, you get a new c that you have to incorporate. And it's going to be very, very rare that you can combine those c's, because every c that you add, the next time you take the antiderivative, you're going to be getting that c times x. And so here we have two constants that we have to incorporate. So as a second example here, if I take the antiderivative of 2/3 x to the 2/3, I'm going to get 5/2 x to the 5/3. So take the derivative of this and you get 2/5 times 5/3 x to the 2/3. And so when you simplify that, you get that original 2/3. And here's my integration constant. And then I'm going to take the antiderivative again. And I have to integrate that, or not, excuse me, I keep on throwing in integration, but we're really talking about antiderivatives. So I make a notation that this is C1x, and then this is C2 that I'm adding for my, because I've taken an antiderivative again. And so that 6/40 simplifies to 3/20, and then my newest exponent is 8/3, and then I have the the C1x plus C2, which are a result of having found two antiderivatives.
So how do you get to C?
That's a good question. Now think about, actually that's a really good question. Let's go back to looking at just the antiderivative where we get a C. Okay, so if I'm gonna, in a simple case, if my derivative is just going to be x, my antiderivative is going to be 1/2 x squared plus c. So think about what derivatives mean. If this is my position, this is my speed, right? And so if I know my speed, I can calculate as time goes on what my new position will be, but I don't know where I'm starting, and that's what this c represents. Okay, so really one way to look at that is if I'm traveling 50 miles an hour and I go an hour, I'm going to be 50 miles from where I've started, but I don't know where I've started. Yes?
So does that mean we'll be given like points on the line?
Yeah, actually, we're going to end up with finding what C is here. Okay, let's go on. Okay, so let's find C. That was a really good, well-placed question. So what we need is one value to set what C is when we're just finding, a single antiderivative. The comparison about the velocity and difference is the best way to think about this that I can think of, where if I know what my speed is, and I know how far I'll go because of that speed, in order for me to find my exact position, I have to know where I start. And so to have this initial point, or some point along the way, we just have this value. And so what we're going to do then is, let's say we have this function that we're going to, we want to find what the original function is, and I'm given the data point that I'm starting, my starting point, f at 0 equals 4. Okay, so the first thing that I do is I'm going to find the general antiderivative, which is, in this case, 3/5 x to the 5th minus x squared plus c, right? So, if I take the derivative of this, I get 5 times 3/5, which is 3 x to the 4th, and then this one we've seen several times, x squared, so I get my c. So now I'm going to plug in my point. F at 0 equals, and I'll put in my zeros, plus c equals 4. Now all of these things, of course, this equals 0, this equals 0, so I end up with c equals 4, and so I know then my function, completely determined, is going to be 3/5 x squared minus x squared plus 4. So I use my initial point to get what that c is. Yes, Marl?
So if you ask to solve for C, you're always going to give us that.
That's the only way you're going to be able to find
Y
c.
equals
Yeah, and it's kind of like, where are you? Well, where did you start is really the answer to the question. So if you don't know where you start, you don't know where you are, right? But it's really the way to think about it, that
Is the
okay, so now let's look at a second derivative. Now a second derivative, you need to have 2 points that you're starting with, right? Because if the second derivative is acceleration, you have to know what your initial velocity is in order to get a velocity function. And to get a distance function, you're going to have to know what your initial distance is. So we have these points, and it doesn't necessarily have to be f at 0. It can be some other point, like this f at 1. Yes?
Is it, for example, it's x equals 3 plus x to the fifth?
Oh, you're right. Let me make that change. Okay, good catch. All right, so we'll take the antiderivative of 8x cubed plus 5, and from there we'll get 2x to the fourth plus 5x plus c. Now here's the tricky part. Make sure that you select the proper initial condition. So the initial condition here is that f prime at 1 equals 8. And so if I look at this where f at 1, so what I have here is this term is when x is 1, I have 2 plus 5 plus c equals 8, so c must equal 1, right? And then finding the next antiderivative, here I have my values, and so I'm going to plug in a 1 here to see what I'm going to end up with. And so if I add my 2/5 plus 5/2 plus 1, I'm going to get 39/10. So I know then that c is going to be negative 39/10 because I want to end up with 0.
Wait, why did you add the 1 to the to f prime after you went from 2x to the fourth plus 5x plus c? Why did you add? Why did
I add
become
up
the
all
1?
these? Because when I'm looking for the value when x equals 1. So I'm going to say 2/5 plus 5/2 plus 1 plus c equals 0. So if I have 39/10 plus c equals 0, then I know that c equals negative 39/10.
Okay, so like if you have CC like the double derivative,
Mm-hmm.
and then you have next to it f of 1 equals 0.
Mhm.
So whenever you have that, then you just plug that in for c, and then you.
Yeah, I probably perhaps should have written this out a little bit more. So what I would do is I'm going to say f at 1 is going to be 2/5, and then of course x to the 5th is 1, plus 5/2 x squared is 1, and then I'm going to add 1, and then I'm going to say plus c equals 0. So what I did on the side was I added these three, and I got 39/10 plus c equals 0. So I knew then what c had to be. It had to be negative 39/10. Okay, so I have a couple to try here, maybe 3. Okay, we'll take the, change that to negative x to the negative 2. Find the antiderivative. And so then when x is 1, then f at 1 equals 2, so c must equal 1, and we get 1. Now this next one is really hard when you think about it, because if we were to take the derivative of something, we get the chain rule, right? And so we know it's going to have some sort of term that involves the square root of 1 minus x squared, but if we take the derivative of it, we're going to end up with 2x on the outside, right? So let's at least attempt this. All right, so let me put this into with a negative exponent, rational exponent, and then say, all right, that would mean that I'm at least going to have the outer function like this, right? And then with my coefficient, and here what I'm going to have is a negative 1/2, but what am I going to put? A 2 or what? Okay, this one plain doesn't work, right? Because we can't, if I did this, what I need to do now is check by differentiating to make sure that I get the right answer. And that's not quite right, right? Because what I'm going to have to do here is, if I'm properly differentiating this thing, I'm ending up with a 2x back here. All right? And I'm introducing something that I didn't have at the beginning. So there is a way to do this, and it's not always simple to do. And we're going to kind of avoid doing this for now. What we're going to do is, on Monday we're going to talk about Riemann sums, Riemann integration, and then we're going to connect it to antiderivatives. And it turns out that there is a relationship between the integral and the antiderivative. In fact, you're probably going to think they're about the same. You know, they are very, very close. And then after that, we're going to get into something called integration by substitution, and that'll be the first really major integration technique that we'll be going over, and that's going to end the course. When you start in on 14, you're going to be taking another lap around the block again. You're going to learn how to take derivatives of things like trig functions, log functions, exponential functions. And then when you get to the integration part, you're going to learn 3 or 4 more different ways of integrating that involve some kind of clever techniques that all have their foundation in things like the chain rule and the product rule. But you can see from this that there's no real easy way to do this. That in fact, it's possible for any kind of function that you've seen so far to take the derivative of. It's very easy to construct an algebraic expression that you can't integrate, or that you can't find the antiderivative. And so, it's going to be a little bit of a cookbook kind of a thing where you have a bunch of different techniques. Some work, some don't. And, we'll just have to be kind of selective about how we choose those. So you'll have some, the homework over the weekend is going to involve finding antiderivatives. On Monday, I'll review the exam. I'll probably put the solution up on Moodle. And then we'll go on from here. We have 2 weeks left. Don't let your other classes get in the way at this point, because these last 2 weeks are hard and they're going to take some study. Okay, so don't think, oh, it's just math. Double down. All right. Talk to you guys later.